Um, it should be okay. She can come on maybe at the end to help answer questions.
Old. I didn't know it could rain in the bay.
Yeah, it's pretty funny. When it rains even a little bit in California, society just like totally shuts down because nobody's used to it. It's like in Canada, it'll rain like, or it'll snow like 3 feet and people will still go to work. But if it snows a little bit on the east coast of the US, everything gets shut down. California is just not built for rain.
I think the UK can do rain, but it can't do snow and it can't do intense heat.
Hmm. Yeah,
Where my
intense heat is something that,
tolerance is very
well,
low.
I guess it's questionable whether California can do it, but we deal with it. Hi, I'm Dan. I'm the CTO here at Goodfire. So at Goodfire, we're a startup that is leveraging all the amazing breakthroughs in mechanistic interpretability to try to change the way that people interact with AI models. We envision a future where nobody deploys models to production that they don't understand. And so to that end, our very early steps towards that very ambitious goal is we've built an SDK that allows you to interact with inside of open source language models. So Llama 3 8B and Llama 3.170B are available over our SDK for you to play with. I'll tell you all about our SDK later. But before that, to get started, I just wanted to talk a little bit about what's motivating this hackathon before kicking things over to Neil. So why is interpretability the most important scientific question of our time? So capabilities in models, I think, as we all know, are advancing faster than understanding and control of those models. There's very few levers to pull to fix issues in the real world when they occur, and they occur constantly. So one of the reasons I was motivated to found Goodfire, along with my co-founders, Eric Ho and Tom McGrath, is from my own perspective, I have been engineering with AI systems for quite some time, and the things that you have to do with AI systems to try to pretend that they behave like normal software is insane. You're doing things like classifying inputs in order to change the prompt. You're doing things like classifying outputs in order to figure out which pipeline you need to route things to. And the entire system is a gigantic mess. And it's only this way because we've just accepted as a prior that AI systems are black boxes and there are no levers inside of them that we can pull in order to meaningfully gain control over the system. So that all changed in the past few years because huge breakthroughs in interpretability, specifically sparse autoencoders and downstream technologies that are being built on top of them, are empowering a new class of technology. And I'm extremely excited about this class of technology. The statement that I would like to make to everybody today is that I think the way that we interact with AI models today is terrible. It's terrible for a lot of different reasons, and it can be better. And interpretability is the core research breakthrough that powers this whole new generation of technology that we're going to see evolve. So everything AI benefits from interpretability. So specifying behavior. When we understand how a model works in the first place, we can specify the behavior that we want from that model much more deeply, much more specifically. We can diagnose issues. If our model's misbehaving in production, we don't just have to fine tune on some new data, cross our fingers, and hope for the best, but we can get to the mechanistic root of the issue. And then another avenue that I'm super excited about is scientific discovery. So AlphaFold, for instance, knows things about nature that no human being knows. Can we understand those insights that AI models have gained into the world and use that to advance our own scientific intuitions, whether that's in biology, whether that's in physics, or whether that's in alignment? So what we've found consistently is when you apply techniques that have been used to help specify behavior, diagnose issues, and discover things with models, and you apply those same techniques that have been working for a decade, but you apply them with a sparse autoencoder in the middle, you just get better results on everything. Where it's like putting the human back in the loop in a pretty extreme and profound way. So the theme of this hackathon is reprogramming AI models. So the question I want to ask everyone before we get started is, what if working with AI was like working with software? Software is many things we wish AI was. Testable, observable, adheres to a specification, and therefore debuggable. So some people will say, well, you can test LLMs, right? But you can only test them in this extremely obtuse end-to-end way. There's no other production system where we would ever, in any type of engineering, where we would ever accept this like level of extremely abstract testability. You want to be able to test the components. You want to be able to modify things. You want to be able to understand edge cases and failure modes. Those are things you can't really do with AI models effectively today, at least not without massive data scale. And so what we want to do is we want to empower everyone working with AI systems to be able to have these tools to make sure that they're developing things that are robust, that are safe, and that work the way that they want them to work. So with that said, I'm excited to introduce Neil Nanda. So Neil, I think, almost needs no introduction, but research lead at Google DeepMind, prolific figure in the field. Personally, someone whose research and whose work popularizing interpretability was really important to me getting really interested in the field and eventually founding Goodfire. So I'm extremely excited to hand things over to him.
Awesome. Thanks a lot for the introduction and for inviting me to speak. So hi, I'm Neil. Um, as Dan said, I'm the lead of the DeepMind mechanistic interpretability team. Tragically, I cannot claim to be the research lead of Google DeepMind, but whatever, give it time. And I'm gonna be trying to chat a bit about sparse autoencoders. What's up with them? Dan, can you see my screen?
It's loading for me.
All right. In that case, I will continue to vaguely say things until I can figure out whether people can see the screen or not. Some people can see it. Beautiful. Um, yeah, if you can't see it, you can click on the link to my slides that I just put in the chat and just attempt to press arrow keys every time I say something that implies I've changed slide. But all right, so what I basically want to try to talk about is how I think about sparse autoencoders and key research results and kind of what I think you should know about them. And the first thing that you should ask whenever you hear about any idea or technique is like, what is the point of this? What is the goal of this? What is the problem this is trying to solve? And from a very, very high level view, the goal of a sparse autoencoder is to understand how language models represent their thoughts, where thoughts is used in a shamelessly anthropomorphizing way. Um, we want we give the model some input, it produces some output, it is doing some kind of computation or cognition along the way, and it has some intermediate things it produces as it processes. What do these things mean? And the 1,000-foot view of what we get from a sparse autoencoder is the ability to give a model some text, like here, I love fish, dogs, cats, and birds, and then see what kind of concepts are lighting up on each token. Where token basically just means word, but if words are long, it gets split into multiple tokens. And we have things like animal-related ones, or punctuation mark-related ones, or affection-related ones. They kind of just act basically as you'd expect. I will flag this is a very simplified interface that is getting rid of most of the concepts that are lining up to make for a nice mimetically fit GIF, but I think conveys the right spirit of what we want here. And one thing I'll highlight is there's this beautiful demo that Neuronpedia made for some open source SEs my team put up called Gemascope that I think is one of my favorite introductions for just playing TLDR for the linear representation hypothesis. Models think in concepts. They represent several concepts at the same time as vectors that get added together. And the goal of a sparse autoencoder is to learn what these meaningful vectors are and to tell you what's lighting up. And the key idea is that we train a specialized neural network to take an activation that we think is some sparse linear combination of stuff, and then try to reconstruct it in a sparse way. What this actually means is we train a tiny two-layer neural network called an autoencoder, whose input is the model's activations, whose thing in the middle is a layer much wider than the activations, and whose output tries to reconstruct the original thing that was given to it. And the thing I've described so far, like, at no point introduces this idea of interpretability or finding the real concepts. But the hope is that sparsity isn't just some coincidental thing that you kind of get for interpretable stuff. Sparsity is kind of inherent to how the model is representing these concepts. And so the hope is that if we can just train a specialized neural network to reconstruct the model's activations without using too many neurons in the middle, there's lots of different ways to regularize this, but all of them are just trying to make it so most of the neurons in the middle are zero. The hope is that the best way to do this is by actually learning the real concepts the model is using, actually producing something interpretable. But I kind of stress all of this rather than like glossing over it, because I think a very important thing to know about sparse autoencoders is that they aren't optimized for being interpretable. They're optimized for being sparse, and we hope that sparsity leads to interpretability. It often does, but sometimes it doesn't, and things can get weird and messy, as I'll discuss a bit later. And yeah, the hope is that each of these things in the middle, they're sometimes called features. I personally prefer to call them latents. You can also call them neurons if you really want to. The hope is that each of these represents one of the meaningful feature vectors. That it has some output that adds to the reconstruction of the activations. This is the meaningful vector, and its activation, like how much it lights up on any given input, is the sparse autoencoder's estimate of how much the model is thinking about that concept. All right, that was the technical thinking hard about how sparse autoencoders are actually trained and what they're doing section. Now I want to talk a bit about what is the evidence? What do we know about them? And my current overall assessment of the evidence is something like, they clearly do something interesting. They find beautiful, rich, interpretable structure in these models. But sometimes they break in weird and unpredictable ways, and they don't behave the way we expect, and they're kind of annoying and janky. And I think there's a lot of further research to be done on trying to make them into as beautiful and glorious tool as I would like them to be. And also, one of the ways we get there is just by trying stuff and seeing what happens. So I am glad there are so many people excited to play around with Goodfire's API this weekend. But, all right, evidence. So Anthropic had this fun paper called Scaling Model Mechanistic. I'm sure many of you have come across it, which has a lot of case studies for interesting concepts found inside the model. A particular one is the sycophancy example. You can look at text that makes it light up, and it's kind of like very over-the-top, gratuitous praise and flashery. You can even use it to kind of causally intervene on the model. You can add in a bunch of the sycophancy feature, and now given a prompt where the model will normally say, "Stop and smell the roses" is not a new saying. What on earth are you talking about? It will talk about what an amazing and brilliant and insightful and fabulous person the human is. This is a cherry-picked example. But the fact that SEs can find stuff like this is pretty damn cool, in my opinion. And yeah, they work on near-frontier models, including finding the same thing for pictures and text. For example, I really like the unsafe code feature that also lights up on the picture turn off safe browsing, and a picture about, do you really want to visit this site? Your connection isn't secure. And I find the fact that they can find abstract things like this very cool. Yeah, as I was saying, they're causally relevant. I'm sure many of you have seen Golden Gate Claude, the beautiful ultimate meme. And it can also be really abstract. A recent paper from Javier Ferrando and Oscar Balcells that I supervised found that models have sparse autoencoder latents representing whether they know who an entity is or whether it's a unknown entity. Like, it knows who Michael Jordan is, so it lights up here, but it wouldn't on Michael Jordan. And the unknown entity latent lights up here. Even on examples of real athletes that the model just happens not to know facts about. And I know, I just find it wild that models not only have internal representations of things like this, but that sparse autoencoders can find them. And we can even use it for things like trying to decode the model's mechanisms, like this delightful paper called Sparse Feature Circuits that looks into things like how the model tries to guess someone's profession by looking at a biography, or how the model figures out how to conjugate a verb. And yeah, so those are a bunch of cool examples of things going well. I also think it's worth dwelling on kind of sharp edges, things that can go wrong, things that can be confusing. And in general, it's very important to bear in mind that when you see beautiful, flashy things in papers, these are generally cherry-picked and tell you very little about, if you pick a specific task and try to use a sparse autoencoder on it, what's going to happen. And you should be prepared for things to go right, and you should be prepared for things to go wrong. A couple of caveats that I think are very useful to bear in mind when playing with this. The first is that sparse autoencoders are unsupervised. What this means is we don't tell them what concepts to learn. We didn't tell the sparse autoencoder, you should track whether you know about an entity or not. We just tell it, find useful sparse things, and we hope that they are interpretable. This means that we, by default, have no idea what the learned features mean. And because it's unsupervised, this also means it can learn things that we didn't expect, which is great. And a very important caveat is that sometimes the features just aren't even interpretable, but still seem to be learned and still seem to be useful. It's very hard to tell whether we're just bad at interpreting them, or if the SE has just learned garbage. But again, it was optimized to be sparse, not to be interpretable, so it's not surprising if this sometimes fails. Second is, it's an approximation. It's an autoencoder. You're trying to find a sparse reconstruction of the outputs, of the activations, but obviously, it's not going to be a perfect reconstruction. And this error sometimes contains quite important information. Just concepts that were important for your task, or that you really want to steer with, that just weren't learned. And they're also a pain in the ass to train, though fortunately Goodfire has put in all the effort for you, so you can be lazy and benefit off all their good work. Thanks, Dan. Um, okay, so a thing you'll often see when playing with sparse autoencoders is they have these labels. Um, Things like, this is a sycophantic praise feature, or this is about coffee or cafe related things. And it's worth thinking about where these actually come from. So, um, the first step is looking at the maximum activating dataset examples for the latent. What this means is we just run the model over a bunch of text. We look at how much the SAE latent lights up on each token in that text, and we then just go and look at the text and look at where it lights up. Here we have an example latent that activates a lot on kind of coffee or cafe related things. And often the word coffee, often things kind of around there. I don't actually have any idea what was up with this line, but probably they're a coworker in a cafe. And yeah, a human can just look at this and kind of make a guess for what the latent does. This is also obviously limited in many ways. Like maybe it's a coffee plus cafe related latent, but when it sees coffee, it activates at like 140 and above. And when it sees cafe stuff, it's more like 100 to 140 because it's a bit weaker. But when you only look at the kind of extreme things, you get misled. Um, and it's also possible to just kind of misread the pattern. Like, when I look at this, I think it's coffee or cafe related things, but maybe it's actually a very specific thing, like cafes in New York, but I haven't read enough of this to notice, or things like that. Or chain cafes, but it doesn't activate for kind of independent coffee shops. Who knows? Um, the way that the standard labels you'll see are produced is typically by giving some of these dataset examples, um, sometimes with kind of things more in the middle, not just things at the top, to a language model and saying, hey, language model, what's the pattern in this? Here's a nice diagram that Transluce made about their autointerp setup. They have a particularly fancy autointerp setup where they have their explanation model generate a bunch of hypotheses. And then they have another model kind of use that hypothesis to predict what the activations should be on some feature text. Scores the explanation according to how useful it is. Because, if you found the real explanation, then your simulator should do a lot better than if you just gave it some random garbage. And use that to choose the explanation that we think is best. On Neuronpedia, I think we just use the explanation model once and don't even score it because scoring is expensive. I have no idea what Goodfire does. Hopefully Dan can explain in his talk or in the documentation. And yeah, so you get these labels. They are often directionally correct. Sometimes they just actually give a very good explanation. Sometimes they can be fairly misleading. You should often try to look at the what we call dashboards, the things with these dataset examples and some other statistics, if there's a particularly important latent you're trying to work with, and you should see if you can get anything interesting out of that. Another example of a theme I've been mentioning a few times, that sparsity is just a proxy. Sparsity is not the same as interpretability, yet it is the thing we optimize for, because it is convenient and quantifiable and optimizable, is this phenomena of feature absorption, from this lovely paper from David Channon recently. The idea behind feature absorption is you have some very general feature, very general concept, like starts with E. And then you've got a much more specific concept, like elephant, as in, this is the word elephant, that always, that if it activates, the general concept will also always activate. Like, elephant starts with E, so the starts with E concept should always be there. This is kind of inefficient, because if you've got a starts with E latent and an elephant latent, and on the word elephant, you now have two things lighting up. This is kind of sensible and interpretable, but it's not very sparse. And so what models can end up learning are these weird gerrymandered features, where the starts with E latent is actually a starts with E except for the word elephant, when I will do nothing. And then the elephant latent has an output vector that includes what starts with E would normally be outputting. And this is weird and cursed, but it is sparser, yet less interpretable. And models totally seem to learn this. So if you ever have anything in some kind of hierarchy, like countries and continents, things like that, be aware that weird shit like this may be going on. Another thing to bear in mind when using SAEs is that the width of the SAE is a very, very important hyperparameter. Typically, what you'll get is there'll be several SAEs of different widths available, and it comes up to you to choose them. And generally, I would say pick the smallest one, play around with it. If it doesn't seem to be working, take the next one up or further up. In terms of what the width means, I kind of think of it as it's like, SAEs are kind of like a microscope. They let you take the model's activations, zoom in, and kind of understand what's going on. And you can think of the SAE width as the zoom level on your microscope. Narrow SAEs learn a bunch of kind of high-level concepts. Wide SAEs learn much kind of narrower, more niche, sometimes more silly and contrived concepts, and also can just learn more. Like, there are some things the small SAEs just do not learn at all that the large ones learn. Here's a nice graphic from Anthropic's Scaling Monosemanticity paper. The big yellow circle is a single San Francisco latent from a small SAE. The green ones are from a slightly larger SAE, where it's kind of broken down into two slightly more refined things, and the blue dots are in a much larger SAE. It seems to have broken down into like much more niche things like articles and San Francisco Airport and random stuff like that. Like, things get more niche. I will also note that we have lots of automatic labels that just say San Francisco, because autointerp is often not that helpful. I'm sure there are differences between these. I don't immediately know what they are. Sometimes it involves digging around, looking at dashboards, or giving the model text myself and seeing what happens. And yeah, I will again plug that I think that the Neuronpedia demo for the open source SAEs my team made is a great thing to play around with to kind of learn a bit more and build intuition. And yeah, I think I will otherwise hand over to Dan. So maybe we have time to take like one question first. Oh no, there have been issues with the screen share for the past like 10 minutes. Alas. Alright, we have one person with a question, I think.
Yes, do you hear me?
Yep.
Oh, cool. Thank you very much for this presentation. I had a question about the SAEs, like on the so slide 45, on the fact that getting with SAEs is splitting more into small chunks of representation. Is it like, have people made a parallel with all the unsupervised paradigm with this kind of knee we can see sometimes on the unsupervised? So when doing clustering, for instance, is it like a clear parallel with that, or we can see other phenomena about this breaking concept?
I think there are some similarities to, like, if you do clustering and you have fewer clusters, you'll get more refined things. It's not quite the same thing, but I think that's like a reasonable starting intuition. Yeah. I don't know when. Sorry. I'll probably do some more questions on the chat because we don't have that much time.
Yes, of course. Thank you.
But all right. Devon asks, why do we care about understanding what the model is thinking about on each token? That's too fine-grained. So my main answer is just, this is just how models work. You just do things on each token. If you want to understand them, you kind of have to understand what's happening at each token. You could potentially aggregate this into kind of more high-level things, and typically you'll be doing something like understanding what's happening at key tokens and using techniques like attribution to figure out which prior tokens matter, but I don't know. We want to understand what's happening inside the model. It is doing fundamentally different computation at every token. You kind of have to look at that if you want to get anything useful out of it, in my opinion. And were there any other questions? Yeah. I think, yeah. To Caleb, as Lovekush says, the magnitude of the vector is not really related to the intensity. Often it's just forced to be always magnitude 1. Rather it's like, what is the output of the SAE from that latent, which is the product of the activation and of the magnitude of the decoder vector. That's like the thing that matters. Were there any other questions? There are more questions. I am currently working on many things, but the thing I'm most excited about is trying to actually find real-world use cases of SAEs, because I think this is important validation of whether they are actually doing anything real versus being misleading, and I am slightly on the fence on exactly where I think they fall either way, though I would be very excited to see Goodfire produce some beautiful products that are just obviously way better than you could do without SAEs. Yeah. Regarding why SEs are hard to train, it's like you're trying to train a very shallow, incredibly wide network, where you want each thing to be off almost all of the time, and this is just kind of a weird learning task, because the main ways to do well on this task are very pathological. They're like, you just have things that are always on and just perfectly reconstructed, or things like that. And this is kind of silly. And so you're kind of balancing between sparsity and reconstruction, and this is kind of complicated. And they're also just kind of computationally intensive. You want lots of data. You need to run it a bunch. Like, to train Gemoscope, it took about 20% of the compute of GPT-3 to train them on every layer and relevant activation. Yeah. Anyway, I should probably hand over back to Dan, because I've spoken for long enough. Thanks all for the questions and interest. I'll try answering a few more in the chat.
Thank you so much, Neil. That was awesome. Yeah, lots of great questions in the chat. Hopefully we can answer some amount of them both now, and then also the Goodfire team will be around all weekend to answer any interpretability questions that you have. So before diving back in, just because we've been having some issues with the screen share, I'm going to share a link to my slides so you can go and follow on directly, just in case this doesn't end up coming through in the stream. Hopefully it does, though. Okay. So coming back to the theme of the hackathon, reprogramming AI models. So building off of what Neil was just talking about with how can we actually use SAEs? How can we make them useful in the real world? At Goodfire, we think that we want to ask the question, what if working with AI was like working with software? So again, software is many things that we wish AI was: testable, observable, adheres to a specification, and therefore debuggable. So I want everyone to just keep this in your mind while I talk about everything that you can do with our SDK. So the Goodfire SDK. What were our design principles when building this? So we should be accessible, yet still expressive and powerful. We want to be a tool that anyone who knows a little bit about interpretability can pick up and start making meaningful progress with, but still make it something that people who are deeply invested in the field can use and leverage to speed up their workflows. So we should empower both research and customer use cases, and we can be the backbone which unblocks a better way of interacting with AI. And there's a bunch of different things that I mean by this, and we'll get into some of them in the course of this talk. So to get started, it's very easy. You just pip install Goodfire, import Goodfire, you get an OpenAI compatible endpoint, something that you're very familiar with interacting with if you've been working with large language models deployed over APIs. And we built a familiar playground. So this looks like a pretty typical prompt playground, but the cool exception is that you can search features and you can edit them in real time. I'm showcasing one of our favorite demo features right here, which makes the model think it's a pirate and always respond as if it was a pirate. So how do we go about finding features over the SDK? So we've exposed a few different verbs that you can use to find features. So the first is just regular old semantic search. And this is the easiest way to get started, just to get a sense of what features are out there. So very straightforward. Once you've instantiated your Goodfire client, you can just do client.features.search. You can pass in a keyword. You can see here I'm searching for pirate, and I get back a bunch of different pirate-related features. And you can see here, for instance, that a rum feature shows up when I search for pirate, which makes sense. Other ways that you can find features that get pretty exciting. So you can inspect the activations for a given input. So in this case, I'm talking to the model in Spanish, and I'm inspecting that input. You can see I get back this context inspector object. And then if I do context.top on that context inspector object, then I get back a bunch of feature activations. So you can see here that there's a bunch of features related to speaking in Spanish, multilingual greetings, also general greetings features that show up. You can see the activation strengths associated with those features. You can also look at individual tokens. So you can iterate over the different tokens. Again, going back to my original input. So I'm having the model respond, hola. I can go and take a look at that particular token, and you can see that there is a feature specifically related to the word hola. But there's also a bunch of other features like saying hello, conversation initiators, informal friendly conversation openers, the model's multilingual greeting or responses. So this is like really already starting to get at what's incredible about features, is that you can enter and you can start inspecting the model with no priors about what you're going to find, and you can find things that you can start making sense of almost immediately. So we've exposed some additional tools on the activation side to help you out. So if you're trying to do machine learning, we'll talk about classification use cases later. Very easily, you can just on that context object called context.matrix, and you get back a big matrix, which shows the features at every token position. So what else can we do? How else can we find features? Another great way to find features is to compare data sets. So in this case, this is just a data set of a single example each. And you can actually get pretty good results here with very little data. But just to fit it all in a slide, there's only a single example here. So you can call client.features.contrast. In case one, I have a totally normal assistant. And in case two, I have an assistant that can't help but make terrible puns, even though my prompt is unrelated. And then I just ask the question, what features are common to dataset one, unique to dataset one, what features are unique to dataset two? And the result I get of this is a bunch of joke-related features. So, the model is telling a joke or offering to tell one, repetitive joke patterns, especially involving common objects or animals. The user's turn to speak in a conversation. The user is posed a riddle or puzzle to be solved. The user is requesting entertaining or interesting content. You may notice that this one in the middle doesn't make a ton of sense. That's probably just mislabeled. So one thing that we want to make sure that you can do is you can effectively debug features when the label isn't quite right. The labeling process is something that we're still continuously improving. And so one of the ways that you can just explore features with even more nuance is by just directly exploring latent space with our SDK. So to that end, we've exposed this neighbors endpoint. The reason that it's an experimental is because we may change this API a little bit before we finalize it in our upcoming public release. But the idea here is that I can grab a feature. So in this case, I'm just grabbing whatever the first feature that shows up when I do a semantic search for animals such as whales. And then I go and look at the neighbors. And you can see that the closest features in latent space to the whale feature are marine ecosystems and coral reef biodiversity, semantic understanding of elephants. I'm guessing that one's actually like just a large animals feature, would be my guess. Naval warfare and ship types, swimming safety and activities for children, etc. You know, all of these make sense, but for any one of these features, like if the label doesn't seem quite right or you're not sure about the label, like a great way to gut check it is just see what's around it in latent space. And we've actually used this exploration to improve and fix some of the labels that we found as well. So now that you can find features, what can you do with features? So first, you can steer, and one way to steer is to enhance a feature. So what I'm doing here is I'm creating a new variant using our SDK. And I'm setting the comedy features that I extracted earlier when I was comparing data sets to 0.3. This number goes from -1 to 1 generally. There's nothing that stops you from going to 1,000. The model just will blow up if you go past 1. Generally, we find that you can get pretty stable effects around 0.5, but depending on how many features you're intervening on, and depending on the specific feature, you may need to tweak this number a little bit. In this case, 0.3 was the sweet spot. So I asked the model, tell me about the moon. And it can't help but make a bad pun. Hello there, the moon is out of this world. Get it? So I've successfully created an extremely punny model. Now, what if I went in the other direction? What if I took those same sets of features and then I turned them off? I set them to a negative number instead. And now I ask the model, hello, tell me a joke. And now I have a model that couldn't tell a joke no matter how hard it tried. I'd be happy to share a joke with you. Here's one. Why did the chicken cross the road? Because it was a clever chicken. It crossed the road to get to the other side. And then it said, ah, I did it. So I've made a model that's extremely unfunny and can't tell a joke. What else can I do with features? So another way I can steer is I can do conditional interventions. This is something that is available over our SDK, which as far as we're aware, no other tools have first-class support for. So what I can do is I can specify something like, all right, how about if that whale feature is firing, even just a little bit, I want the model to talk like a pirate. And now you can see, I asked the model, tell me about squids. Squids, they're some of the most fascinating creatures in the ocean. And then I asked the model, talk to me about whales, and it says, whales me hearty. They be the largest creatures of the 7 seas, don't you know? So yeah, we have the ability to specify even more nuanced behaviors. You can nest these, you can do all sorts of crazy things with it. And we're very excited to see what you all build with this feature. So one thing to note in the steering use cases is that what makes steering really unique as compared to prompting is that steering is continuous. You're leveraging the model's own intelligence to get smooth behavior as you vary the feature strength. So you can see here this nice graph of as we turn up a conciseness feature, the mean response length in characters goes down fairly linearly until you hit some point, and this is true for a lot of features, where the quality of the response begins to degrade. But we've curated everything, so 0.5 should be the sweet spot for most features to at least start to get a pretty stable response. And you can see if I go the other way, if I start to go negative, the response gets longer and longer. This is one of the things that really suggests to me that we're really on the right track with sparse autoencoders and features, is that we just get these smooth, beautiful looking curves as we intervene on the model. And then the another example, just quickly over here, is you were looking at 2 different features, varying them at different strengths. These are both features which mediate conciseness in some way, and we're studying the interaction of these 2 features together. And you can see that there's sort of a spot where the features do have a complementary effect. But also, one feature, this conciseness feature 1, has very little effect without conciseness feature 2 also being present. And this is an LM as a judge setup on the right that we're measuring. Okay, what else can you do with features? Classification. So one of the really exciting things about features is that, again, we have these generalist models, and to some degree, like, we're letting a lot of their potential go to waste because we're not using the richness of their internal representations as like first-class citizens of interaction with the model. And so one thing that you can do is you can extract features and you can train classifiers on them. So on the left here, I've trained a decision tree, and I love using decision trees for this because you end up with these extremely human interpretable like ontologies for the classifier, which are pretty remarkable. So in this case, this was a financial data set. So the task at hand was, here's a bunch of news, financial news. You have to classify whether this is good for investors in the company that's being talked about or bad for investors in the company that's being talked about. And so you can see what happens here. Okay, so if the ending or terminating relationships, employments, or accounts feature is active, that's probably bad news for investors. All right. We'll get back to this like financial statistics and numerical value feature in a second. But then down here, suppressed or internalized negative emotions. If this feature is active, then it's negative, obviously. And then this financial and statistical numerical values, at first I was like, what does that mean? That's really interesting. But notice that if the feature is like below some threshold, it's very likely to correlate with negative responses. And so ultimately, I looked at this feature. I looked at a bunch of examples for when this feature looked up. And it turns out that this feature fires more strongly the more precise a number is. And it turns out that in positive financial news, you're often going to say things like, things grew 8.89%. But in bad situations, you're much more likely to just round to the nearest integer, like profits declined by 10% or whatever. So this is a really fun example to me because it was something about the world that once I thought about it, I realized like, oh, that's actually totally true. That would be a totally reasonable heuristic for a classifier to learn. But because of how interpretable our sparse features are, I actually got to learn something new about the world in the process of just studying a pretty, simple classification task. And then on the right here, we have a example of doing PII masking. So we're able to train like pretty generalizable PII detecting classifiers on the activations of individual tokens. So I'm personally also, the steering use case is extremely exciting. The classification use case is extremely exciting. And we've built tools to like support both of them really well. And I'm excited to see what everybody can come up with. And then another thing I want to talk about is visualization. So there are 4 notebooks that we've sent over. There's a quick start notebook, an advanced techniques notebook, a classifier notebook, and then there is something called the latent explorer notebook. And this is a 3D visualization of feature space that we've built. So feature space is obviously very high dimensional, and we need to collapse it a little bit to start to make sense of it. So in this case, I use the neighbor's endpoint and a little bit of dimension reduction in order to create these 3D visualizations. In this case, I'm looking at whales and their characteristics. And as I kind of rotate around, you can see that there's definitely structure here. And if I explore the structure, the features, they tend to make sense. So like one of these directions has to do with the ocean. One of these directions has to do with large animals. I found one of these directions has to do with intelligent animals. So it's really cool to just explore and see what you can find about features and what they tell you both about the model, but sometimes about the world. So I'm extremely excited to see what everybody builds with it. Like, this is why we built this technology in the first place, is to put the power of interpretability in the hands of people like you. We're around all weekend to answer questions, help you build all of your exciting projects. I was looking over in the projects channel, and there's some really cool ideas in there that I'm really excited to see the results on. And so real quick, just always be plugging. So if you want to understand your models, contact us at contact@goodfire.ai. And we are hiring awesome scientists, engineers, and general interest team members. So if you want to join us, head over to our jobs boards at Greenhouse, or you can also scan this QR code, get there from just goodfire.ai. So extremely excited to see what everybody builds this weekend. Thank you so much, and let's get hacking. No problem. I just said no problem. Yeah, I'm happy to answer. Yeah, so as far as like evaluating steering is concerned, this is something we spend a lot of our time doing. I think what you'll find using our API is that we have made steering significantly more reliable than any of the other tools that are out there for steering, just because we've spent so much time and research energy on that specific question. Um, there's still a lot more work to do, but I do think that this is a problem that a lot of progress is going to be made on really quickly. I think Anthropic that post that they did was is like a really good like way of looking at it. It's like off-target effects are definitely a thing that can happen with SAEs. And finding the sweet spot for an intervention is still a little bit tricky and not something we fully locked down. But I think we've made a lot of strides there too. And also like further exploring this would be a great idea for a hackathon project. I think as far as like suggested prerequisites for participating in the hackathon, what we're trying to build with our SDK is we're trying to make interpretability accessible and something that you can pick up easily. I would just start by looking at our quick start notebooks and seeing if there's anything in there that's exciting to you and just taking it from there. If you know how to code, then you should be able to pick up what we're doing. There's more advanced techniques that may take a little bit longer to fully understand, but I would encourage everyone to participate. I think that further progress in interpretability will be accelerated by more people just having access to these core technologies. Yeah, so our SAEs are trained on chat data. So the use case that we've optimized for here primarily is sort of chatbot use case. Uh, you could train SAEs on all different types of data sets, and that's something that we're going to do more of in the future. But for these projects, like focusing on chatbot use cases, you'll have the highest resolution features there. So yeah, so there's a question about for the hackathon, are we more interested in specific features in the interface or programmatically finding features for a specific task? To which I'd say, I don't know, do what inspires you. Like we're trying to build a generalist tool to ask interesting questions with. So I would encourage everyone to just like follow their interest. This is a new field that's unfolding all the time, and we just want to make it possible to do meaningful, exciting work with these tools. There are rate limits. You can see the rate limits in the docs. If you have a reason to ask for a higher rate limit, you can reach out to the Goodfire team. We are capable of raising them, but make sure that when you ask for a raise, you include what the problems that you're running into are. That way we can set it appropriately for your use case. Um, so we have a number of beta customers doing lots of different things. We're under NDA, so I can't go into too many details, but I think that the applied use cases for interpretability are as expansive as AI itself. Once the form is submitted, we're actively going through and adding people to the platform. We'll do this in batches. So everybody who's already on the call today, you should have access within the next hour. And then you can get hacking right away, hopefully sooner than that. But for everybody who submits the form after the meeting, we'll just be checking periodically, probably every couple of hours. We'll send out a wave of invites. So there's a question about, can I say more about how positive and negative features are encoded? So features are just directions in latent space. We as like people might enter with like preconceived notions about semantics. And the model might not represent semantics exactly the way that our preconceived notions are. So a really easy example for me here is that there isn't really an English feature in Llama. Llama is in English by default. There are features that represent other languages, other modes that Llama could be in, but if a other feature isn't present, then it's in English. That's just the default behavior for Llama. We can reason about that. Probably has to do with the distribution of tokens that it was trained on, et cetera. But it's the case for Llama. So there are features that, like, from our perspective, from the ontology that we'd be comfortable with, like, that may look like you're adding something when you're thinking of it as removing something, and it may look like you're removing something when you're thinking of it as adding something. But if you look at the label, you reason about the label. If you give a positive value when steering, you're steering in the direction of the effect of the label. And if you give a negative value, you're steering away from the direction of the effect that the label implies. There's a question. Yeah, I think honestly, I think one of the really fun things, like one of the reasons I fell in love with Interp is that you kind of have to meet the model on its terms, and eventually, often, if you're staring at a problem for long enough, like it makes sense, but it's not always making sense in the way that you entered with a notion of how it should operate. Do I recommend nudges or pins for steering? I recommend nudges, generally speaking. I think pins are better for studying certain types of behavior because for context, the difference is that nudging takes information about the context into account, whereas pinning is just saying this feature is on all the time, no matter what. So generally, if you really want to like study like specific features and like the effects of them at like different thresholds, and like you're okay with a little bit of decoherence in the model, pinning would be the way to go. If you're looking for more expressive generalized behavior, then nudging would be the way to go. Um, our SAEs are trained on layer 19 in Llama 3 8B and layer 39 in Llama 3 70B. We chose these as the layers to expose for our hackathon because the middle layers of the model are the most representationally rich. So yeah, we just got the coolest features. So I have been able to make it speak like a Spanish pirate before. Someone's trying to make the model speak like a Spanish pirate. That is actually possible. I've done it. I think like you may have to find the right Spanish features. You may have to find the right pirate feature. You may have to like set the right levels together. But I have been able to replicate that specific behavior. Yeah, that sounds great. And yeah, so I'll answer what I can. As we said, we're around all weekend. Like, we just want to make sure that everyone is building awesome stuff with Interp. So how many features are there in total? About 65,000 exposed over the API right now. You can't easily iterate over all of them with the labels. However, you can get a matrix for any given input in a data set. So you could look at them that way. The question about the layer, they're different layers for each of the models, but they're representationally rich middle layers. Awesome. Thank you so much, everyone. Excited to see what you all build.
Hi, yeah, actually, I'm gonna have to sign off pretty soon, so I was just jumping in here to, so I can leave a message on the text side. Yeah, so maybe I'll keep up with people via messages, but yeah, I'm not going to be in the call. All right.
Awesome. So I think I'll yeah, well, I guess I'll come in and like check in and answer questions throughout the day. Does that sound good? Yeah, thank you. All right, cool.
Find you.